Now let's look at 3.3, regular singular points. So first, we're going to define different types of singular points. And the differential equation we have is the second order homogeneous equation. Let's suppose x equals a is a singular point. Now, if x satisfies the following two conditions, which is the limit of x minus a times px, which px is the coefficient of y prime, is equal to a constant, and limit x minus a squared times qx equal to a constant, p naught and q naught. If that's the case, then we say x equals a is a regular singular point. Otherwise, we call it an irregular singular point. Let's look at some examples. First equation, this is called Bessel equation of order n. It has this form. Now, if we divide both sides by x squared, then we see that x equals 0 is a singular point. Now let's check whether it's a regular singular point. So we can going to look at the limit as x approaches the singular point, which in this case is 0, x times px, and px, remember, is the coefficient function of y prime, so we have x times 1 over x. That equals a number. So the first condition is satisfied. Then we look at the second limit. It is x minus 0 squared times qx. And we see x squared cancel, and when x approaches 0, this is negative n squared. So it's a number. And because both conditions are satisfied, then we say it is a regular singular point. Let's look at another example. We have given the general equation of order n, which has the following form. So again, first we want to make the coefficient of y double prime be 1, so we divide both sides by 1 minus x squared. And we observe that singular points are plus and minus 1. Now let's check whether there's regular singular point. So let's first check x equals 1. So we're going to look at limit x approaches 1, x minus 1 times px. And px here is and we can factor the denominator And if we distribute -1 inside here, then this becomes 1 minus x, cancels with 1 minus x in the denominator. So we have 2x. When x goes to 1, approaches 1, this approaches 2 over 2, so approaches 1. And then check the second limit condition. Qx is this fraction. And again, we can factor the denominator. As, I'm going to write it directly as negative x minus 1, x plus 1. So in this case, x minus 1 cancels with x minus 1. So we have limit now as x approaches 1, here denominator approaches -2, numerator approaches 0, so it's 0 over -2, so 0. So again, both limits equal to a number, therefore x equals 1 is a regular single point. And I'm going to leave x equals -1 for you to check. And the conclusion is you get is it is also a regular singular point. Okay, next we're going to look at Fubini theorem. Here, the reason we want to talk about regular singular point is because a differential equation having a singular point at 0 ordinarily would not have power series solution of the form summation cnx to the power n. So the straightforward method in section 3.2 fails in this case. So we want to figure out some other way to represent our solution in power series. And Fubini's theorem here gave us a way to represent our solution in terms of power series. So let's assume x equals 0 is a regular singular point of the following differential equation. And let's let R1 and R2 be the roots, and we order them so that R1 is bigger than or equal to R2. They are the roots of the initial equation, which is given by this form, where P0, Q0 are the values of the limits. Then the first conclusion is there must exist a solution of the form x to the power r1 times a regular power series, where r1 is the largest root. The second conclusion is if we check the difference between R1 and R2, if this difference is not zero nor a positive integer. So for example, if R1 minus R2 is equal to 1/2, then there exists a second linearly independent solution of the form x to the R2 times a power series. Okay, and where R2 is the smaller of the roots. Now, I want to make one remark about regular singular point being at 0. There's nothing special about it. So if x equals a is a regular singular point, then we can translate it to 0 by making the change of variables t equal to x minus a. Then it becomes the same problem that this theorem talks about. So we can still apply this result to problems where the regular singular point is not at 0. Okay, now let's look at example. So we're given this second order equation. Let's divide both sides by 2x squared. So we have our px here, we have our qx here, also including the sign. And we can see x0 is a singular point, so we're going to check this point. And here we can see both numerator and denominator x squared, so this is 3/2, and that's our p naught. And then checking the second limit condition. Qx. So denominator cancels, when x goes to 0, numerator goes to -1, denominator goes to goes to 2. So Q naught is -1/2. And then we can construct the indicial equation, which is given right here. So we have r times r minus 1 plus p naught is 3/2 r plus q naught, so minus 1/2 must equal to 0. And then simplify this, r squared minus r plus 3/2 r minus half equal to 0. So that's r squared plus 1/2 r minus 1/2 equal to 0. And we can factor it as r minus half and r plus 1. So we get r1 is, remember we want to have r1 to be the largest and r2 to be the smallest. Okay, so next time, this is how we can solve an integral equation. And next time, we are going to use R1 and R2 to construct Frobenius series solution.